We are live.
Yeah, good morning, everyone. Welcome to this MLSS session. We are now very happy to have Marco with the second talk about optimal transport.
So good morning or good afternoon or whatever time it is where you are to everyone. Yesterday we had this introduction to optimal transport, which was a bit of math, but also a bit of hand waving. It was also a lot of promises. I was basically trying to advertise for optimal transport as a theory and saying it was useful and trying to give you a hint of why. Now the session will be more about computations. And I hope you will see there's a bit of everything: exact computations, approximate computations, algorithmics. I hope with this survey you will have a better understanding of how this can be used in practice and where you should start to code. So the first part will be about computing optimal transport exactly. And this includes basically cases where there are closed form solutions. Then I will describe the more generic solvers to solve optimal transport when you use them on discrete measures. There is data, real data, not just densities. And I will show that there are a few issues there. And this will provide the transition to the third part of the talk, which will be about regularization. So the first thing you should notice when you're dealing with optimal transport is that unlike other classic divergences such as Kullback-Leibler or even the L2 distance, it's actually very meaningful to define, or still meaningful to define optimal transport regardless of the structure of the measure. I'm talking here more particularly about the Kantorovich problem, the one with the linear programming formulation, because you remember that no matter what the measures that you're dealing with, we are going to be able to come up with couplings. And so those will be discrete couplings, semi-discrete couplings, that is discrete on the one hand and continuous on the other, or continuous couplings. And for each of those three settings, basically Kantorovich formulation works, at least on paper. So it's more a matter of how to compute it. But it is actually well-defined. So unlike, for instance, the Kullback-Leibler divergence that blows up if the support of the two measures do not overlap. So for each of those three cases, there has been progress and works. And so I gave here a few pointers. Please notice that in the PDF, this would work as well. Each of the citations that I'm providing here points to a link. So in the discrete to discrete world, where we're comparing two discrete measures, so this is very much like the soldier's case, the example of Kantorovich that I showed earlier. Then we know, and I will show that there is a family of solvers to actually compute exactly optimal transport, but it's costly. And those solvers are called network flow solvers. In the discrete to continuous, or vice versa, or continuous to discrete case, the problem is a lot more complicated. And as you can expect, it's either going to work in very low dimensions in which you can have a nice grid approximation of your continuous measure. So there have been a lot of works by, especially by Quentin Mérigot and Bruno Lévy, who have provided solvers that work in 2D or 3Ds, for instance, when computing semi-discrete transport between a sphere or a ball and a set of points. And this is important in some applications of transport. There is an application called reflector, computation of reflectors. But if you are in a higher dimension, as you can probably see, we will need some form of stochastic optimization. We will need to sample from this continuous distribution. We won't be able to actually use it as a whole. And if you're transporting from a continuous to a continuous distribution, this is more the setting that people like to consider in PDEs. And this is more also the setting that you will see in most mathematics books. This is where it is typically covered. And one numerical approach to handle this, also in low dimensions, is a very famous scheme called the Benhamou-Brenier scheme, which I won't cover, but which essentially handles transport as a dynamic problem, trying to find time step after time step how the mass moves optimally from this density to this density. So I will essentially cover this part in these lectures, because this is a bit what numerically most methods boil down to, except for the Benhamou-Brenier formulation. So there is also something important, which is that There are cases in which optimal transport is solved. We know that it has a closed form, and it's actually an easy one. And this has actually inspired a lot of follow-up work recently. So I will explain a bit more what kind of follow-up work. But the statement is as follows: if you are comparing distributions on the real line, and if your cost is well behaved in the sense that it is a convex function of the difference between two points on the real line. So this could be, for instance, any cost function c of xy, which is a univariate function of the difference between x minus y. So this will be of an overload here in the operator. It's basically any function that takes the difference between x and y and applies a convex function on top of it. Then, if C is convex, and you write f minus 1 mu, f minus 1 nu, the quantile functions of the two measures mu and nu, the Wasserstein distance with this cost, or the optimal transport problem solved with this cost between mu and nu, is going to be the integration of this C over the quantile of the two measures. So let me illustrate this a bit. Imagine I have this density here and another density here. And they're both supported on the real line, and actually they both take values between 0 and 10. Now, what is the CDF? So before getting to the quantile function, we usually start with the CDF. The CDF is the cumulant density function. It's basically the integral of this density. So it's going to be for every value x here, the area that is left on the density on the left. And so this is what it looks like. Okay, so obviously mu starts quite quickly and then starts to plateau here. So basically the CDF goes up very quickly, and then from 5, let's say, it starts to plateau. It reaches slowly its value at 1. And here the opposite applies for nu. Here we have three modes, but there's nothing much going on in the first 5 segment between 0 and 5. So it just accumulates a little bit of mass, and here we have 3 waves that say that basically the CDF is climbing up to 1. So here we go between 0 and 10, and here on the y-axis we go between 0 and 1. And as you know, the quantile function corresponding to those measures is simply the inverse of that CDF. And so by inverse, I just mean the symmetry. The symmetric function, it's as if you were just symmetrizing around the axis a equals x. And so what you get naturally, if here the y-axis was between 0 and 1 and the x-axis was between 0 and 10, you get something that is between 0 and 10 in the y-axis and between 0 and 1 in the x-axis. And so the main insight that you get here is that when you want to compare two densities, rather than do something that looks a bit like KL or L2, which would be compared directly the densities as functions themselves, you first do the transform, that you take the density and turn it into a quantile function. And so what is exactly the advantage of this? Well, a quantile function representation is very handy because it allows you to compare the values of the support of the two distributions, but in a clever way. That is, we're going to compare the median with the median, the quartile with the quartile, the third quartile with third quartile, etc. And so once we integrate differences in those two quantile functions in all the values that we have, which is between 0 and 1, we get exactly the Wasserstein or the optimal transport problem associated with this cost, whatever it is. So I'm going to simply look at every difference between the quantiles of mu and nu, and in the end, I would just apply this function c to the difference and then integrate. And so the first remark that the first simple thing that you can notice is that if you're taking c to be here the identity, so this is just the difference between x minus y, then what you get is you're just summing the area of the difference between those two curves. And the fact that you sum it here between quantile functions or between the original CDFs is the same, because it doesn't change whether you're integrating this way or this way if you're taking C to be the identity. And so the difference between quantiles will be the same as the difference between CDFs. And this is also the Kolmogorov-Smirnov, the distance between CDFs. However, when the cost function is something more general, this equivalence doesn't apply anymore. And the other important thing that one needs to notice here is that actually the Morse map, remember the one that is the Morse was after, was trying to find, which takes the real value and outputs the real value, is actually given to you in closed form with this formula. It is simply, so if you were to, so here maybe I should have given it in the other direction, because here I'm giving it in the direction where nu maps to mu. I should have maybe given it as f-1 nu around f mu. But it basically does the following. It takes a value in the support of a measure, computes somewhat a key for that value, and the key is between 0 and 1. It's the where it stands in terms of percentiles, of the quantiles, and then use that key to compute, to output the quantile of the second distribution. So remember the very first problem that when I was playing with the Earth in 1D, well, actually it's solved in closed form. You just need to compute the quantile function of the first measure, sorry, the CDF of the first measure, the quantile function of the second measure, and then do this kind of lookup process. And let me also say that more generally, for functions C that are such that, which are known as submodular, such that basically the cross derivative here is always strictly negative, this also works. So all of this, you should remove basically the C applied to the differences and directly put C off the first quantile and the second quantile. So it's quite general, and this is useful because people have considered something called the sliced Wasserstein distance in recent years. So this was originally proposed in the paper by Julien Rabin and colleagues. And interestingly, I think the sliced keyword doesn't really appear in the title. So this was more of a byproduct of their work on computing barycenters cheaply. And here is what they do. Here's what they propose. They essentially say, if you give me two measures, mu and u, which are now in high dimensions, I am going to project them randomly. So theta here is going to be a vector on the sphere. I'm just going to project the measures randomly onto a line, and I'm going to look at the distribution of the values that I get out of those projections. And then I'm just going to compute the standard Wasserstein distance between, or optimal transport between those two measures, but when they are basically projected on the line. And then I'm going to average this over several possible directions. So the directions can either be random, or more recently, people might be interested in trying to optimize those directions. There's also been work with a student of mine on not only considering single lines, but hyperplanes. But then the computations become more complicated. But sorry, let me just say then that this sliced approach is quite popular in machine learning because it has a lot of benefits. It's computationally stable and easy. I mean, it's easy to compute, and it also shows nice performance in some applications. So this is a particular case, easy case number one. The easy case number two is Gaussian measures. So this is another exciting, nice case because that has spanned quite a few applications. So if you heard about the fresh inception distance in GANs, this is basically using this formula. So I'm going to switch the setting. So now omega is in RD. So it can be any dimension D. It could also be a Hilbert space of infinite dimension, actually. All of what I'm going to say here works for Gaussian operators in Hilbert spaces. So if omega here, for simplicity, is in RD, and the cost is the squared Euclidean distance, so this is an important limitation, and you have two Gaussians, mu and u, and each of them is specified by its mean and its covariance matrix. And I'm not really going to assume yet that they are invariable. So those might be degenerate Gaussians. Then the Wasserstein distance between those two measures is very simple to picture. It's first just simply the difference between the two means. So somewhat you can basically just reduce the difference in location to just where the means are located, plus something which depends only on the covariance matrices. So it kind of splits the information into two parts. And this something is called the burst metric. And the burst metric is this object. So the burst metric squared is, I should probably put the square here to be fair. So the Bayes matrix square is the trace of the first covariance matrix plus the second covariance matrix minus 2 times something which looks like an average of covariance matrices, and here to the square root. So it's the square root of mu, sigma nu, square root of mu again, and the square root of all this. There are alternative ways to write this quantity, and so if you look at the papers, you will see there's quite a few identities that you can play with, but this is the most usual definition. So one thing you can notice, and that's not obvious if you think about the KL, for instance, is that when sigma mu and sigma nu go to 0, so if you have Gaussians that are degenerate and that collapse, well, first, this thing, of course, is 0. It's going to be 0 plus 0 minus 2 times 0. And so this will basically fade to 0. And so you will get that when you have two infinitely thin Gaussians, their distance in Wasserstein 2 cents is the difference between their means. Whereas if you look at the Kullback-Leibler divergence, this blows up. Okay. Another very nice result of all this is that basically this quantity here doesn't come. I mean, after too much tedious calculus, it actually comes from a simple observation and using the Brognier theorem. So the first thing is I am going to claim, and I'm going to try to prove it in the slide, that this mapping is optimal. And so let me parse the mapping for you. It's anything that takes a vector in RD and applies it and outputs the mean of the second measure, the target measure, plus a linear operator times x minus the mean of the first measure. And what is this linear operator A? It is something now that needs the invariability of mu. Not yet of nu, but it needs somewhat that the input measure, the one you're starting from, has a full volume as a covariance matrix that is not degenerate. So it's going to be the square root inverse of sigma mu times this matrix, which appears here, if you remember, times the square root of sigma mu here. And so why can I claim that this mapping is optimal? Well, the first thing you should notice is that if you have a random variable that is distributed according to a normal Gaussian distribution with m and sigma, then if you just take a linear transform or a affine transform of this random variable, then you also get a Gaussian. And this is well known, of course. And basically, the Gaussian will be such that the mean is multiplied by C, and you add a B, and then the covariance is going to be impacted by multiplying on C on both sides. Now, if I had a white blackboard, I would basically show you that this mapping here is essentially such that if I take X to be distributed according to the first measure, the first Gaussian, then this affine transformation of X will be distributed exactly according to this second Gaussian. So you can start playing with this. So if X, if you have a CX plus B, so here basically I'm going to have I'm adding a mu nu. So here this will appear here, and then this is centered. So this will have mean 0. So basically the mean of this Gaussian will be mu nu. And now what is important is looking at what happens if I take this matrix and I multiply it both on the left and on the right by this matrix. And you should see that if this is basically sandwiched on both sides by this twice, on the left and on the right, first the sigma mu will disappear, and then basically everything will collapse up to the point that we only recover the sigma nu here in the end. So this is quite easy to show. It's just that we crafted this linear operator so that basically the output, the covariance that we get in the end is exactly this one. Now, why can I claim that this is an optimal mapping? Well, I can claim this is an optimal mapping for the following reason. So let me just help you visualize a bit. Here, this is real data. I mean, real measure. This is a Gaussian here. Those are the level sets of the Gaussian. This is another Gaussian with another level set. So basically, what this mapping is doing is whenever I take a point here, I'm taking it, I'm moving it here. Okay, so this point here is moved. This is the Monge. This is a few arrows describing the Monge process of a worker taking the mass, whatever mass is here, and put it in there. Now, why do I claim that this is an optimal mapping? Well, the reason I can claim this is thanks to Brognier theorem. You remember that I told you that the Brognier theorem tells us that if we have two densities and you can go from one to the other using the gradient of a convex map, then necessarily the transport, that movement was optimal. And so that mapping here was optimal. So the only thing we need to check now that I found one transport, a way to actually go from the first measure to the second measure, the only thing I need to check is that this thing here is the gradient of a convex function. And remember how it is defined. It's just an affine function, and the linear part here in this affine function is just this matrix, and this matrix is obviously positive definite. It's a positive definite matrix here, two roots, a root which conserves positive definiteness, and the multiplication on the left and the right by a positive definite matrix. So essentially,
Marco, let me stop you for a minute. We cannot see your cursor somehow. So
you cannot see what the cursor?
Yeah, exactly. So
okay,
things we do not see it at the moment. I don't know why usually it works, but
yeah, I think I know where it comes from. Let me just try to fix that.
You have to change it on Keynote, our expert says.
On preferences in Keynote or directly? Okay, yes, exactly. So I think it's here. So it's preferences and it's probably
yes.
And then it's slideshow.
Provide the expert advice.
Exactly.
It should be just one click. I don't see your preference, but is it?
Yeah, I think it's now. Do you see it?
Yeah.
Now we see it. Thank you.
Okay, great. Sorry. Thanks. I switched computers between yesterday and today because Keynote crashed yesterday. So I hope this one, on this one, it won't. Yeah, so what I wanted to say is if you take this, I mean, if you have this mapping, this is the example, you know, of displacements. And so if you look at this map, essentially, what you see is that this is an affine function, and this matrix A here is by definition a positive definite matrix. We're basically playing with a positive definite matrix here in the middle, two left, right, and then left, right, and then square roots. All of this conserves positive definiteness. And so, sorry, you can obviously write that, oh, I'm sorry, this is not upside, this is an F. That T here is the gradient of a function F, and my function F here is just simply this thing. It's just the quadratic form associated with A plus MB, sorry, there is small notation inconsistency here. This would be a beta, so a mu and a nu. So it's just basically taking a linear function of X, a quadratic function of X, and then actually you could put whatever constant you want, of course, to recover that this T map is the gradient of this function F. So I apologize. Let me just recap. This should be F. This should be mu, and nu. So in this picture, I'm actually plotting the true potential, this F function here, this quadratic form. So again, this was the mapping seen from above. This is just where the masses should go and where you should instruct the worker to move the masses. So of course here I have arrows that go outside of this plot because the density is going on and on, right? They're supported everywhere. So any place you want on the plane, you will find a target for the mass. Here, if I'm changing a bit perspectives, this is still the same, exactly the same distributions, a peaked Gaussian and a flat Gaussian. This is still the true mapping. But what you can see is that you should interpret this mapping here that is happening on the plane as the gradient of this potential. And this potential is this quadratic form that is plotted here. So this makes it very convenient to do transport between Gaussians because essentially the Monge maps are always linear, affine maps, and they are given in closed form with respect to Gaussians. So let me say this doesn't extend to mixtures of Gaussians, of course, but it does extend to an interesting family of distributions, which is called elliptical distributions. So it's basically any family of distributions that have elliptically contoured, that are elliptically contoured. So for instance, this includes uniform distributions on ellipsoids or many other kinds. And in that case, still the same result applies. That is, the linear map is still the optimal. A linear and affine map will still be an optimal Monge map. So this is a bit of an illustration. This is also something that's actually plotted exactly. Here we have an ellipsoid which has a certain covariance structure. Here we have another ellipsoid that is a bit different and located in a different place. This is an ellipsoid that is degenerate. It's basically just a point with a zero ball around it. And this is an ellipsoid that's degenerate because it only takes values on the plane. And this is a super degenerate ellipsoid because it only takes values on the line. And for each of those things here, basically the distance from this ellipsoid to all of the other ellipsoids is the same. So here we have a 3D rendering of how far it is for of objects that are equally far from this original object here. So we can compare degenerate Gaussians with this setting. An interesting direction is, however, that the Monge map itself might be degenerate, however. So if you want to go into the details, this here always works, regardless of the invertibility of the covariance matrices, but this here won't really work. And so this is here we're touching the frontier, you know, between Monge and Kantorovich, where in some cases you can actually solve optimal transport, but you cannot solve for an optimal Monge map. You may not always have a Monge map. So to be more precise, there is going to be a Monge map to go from this ellipsoid to this segment, but there's no Monge map to go from this segment to this ellipsoid. And you can't grow in dimension with a Monge map. You're just restricted to staying where you are. So now the other family that is, I mean, the other setting that is now mostly relevant for people in data sciences is when you're starting to play with Dirac masses or discrete measures. And so here, this is the most simple discrete measure you can think of, and it's just 2 Diracs. And a nice thing about the Monge, the Kantorovich formulation of optimal transport is that here you can compute it in exactly, and it's very simple. If you have 2 Diracs, there is only one coupling that couples them, and it's the Dirac standing at xy. Okay, if you had the picture, you know, where you have the 2 measures. Try to picture something that sums in one direction to the first measure and in the other direction to the second measure, where it's just the Dirac that is exactly located at xy. And so you're going to integrate the cost against that coupling, which is Dirac of xy, and that's just going to be distance or cost between xy. So to summarize this slide, if you have a cost on the manifold or whatever, when you use the Wasserstein distance, you're basically trying to lift from points to distributions. And the nice thing is that somewhat the Wasserstein distance is consistent in the sense that if you look at points no longer as observations on the manifold, but as Diracs, as degenerate probability distributions, then the distance between those 2 probability distributions is still going to be the same as the distance between the points in the original space. Now, when you start adding more Diracs, of course, this gets a bit more complicated. But here there is a link that is very easy to understand with classic CS, computer science, which is that actually optimal transport in this case is equivalent to an optimal matching problem. And so what is an optimal matching problem? It's just a way of saying, if I have 2 point clouds of the same size and with uniform weights, then the optimal transport is about trying to, so let's say this is the problem with the barracks and the soldiers, the soldiers and the front lines, where every barrack has 10,000 soldiers and every front line point needs 10,000 soldiers. So then you just assign 1 barrack to a front line. And this can be solved. You can see this as a problem of a space of permutations, but it is simplified by using linear programming and solving it on what people call the Birkhoff polytope. But this is just a particular case. Let me just focus more on the general case. So in most applications of optimal transport, what you will be dealing with is this. You have a point cloud on the left, maybe weighted. So here I have n points, and a point cloud on the right, which will also be weighted, but typically will have more or less points. it's very common that you have point clouds of different sizes. And so you have different weights, different sizes, and then you want to solve for this optimal transport problem. And so we somewhat go back to the example with Kantorovich. And what I try to explain a bit intuitively, I'm going to lay out more rigorously here in formulas. So what is really important to notice is, just as the Kantorovich problem highlighted, there's going to be two things that we're going to look at. The first one is the geometry of the problem, meaning how are red points situated related to the blue points. And this is going to be basically how costly is it to move mass between any pair of red and blue. And then we're going to look at the height, the masses, and we're going to put it a bit apart to formulate this problem. So we're going to have, on the one hand, a metric or geometric information contained in a matrix of size n times m. This is just going to take into account where the points are, and it's going to compute a distance or a cost. Here, I put the distance to the p to be consistent with the Wasserstein notation, but actually it could be any cost. So it's going to be distance xi, yj's, okay, so pairwise distance matrix. So people in kernels, for instance, are familiar with this way of thinking. And we are going to take apart the masses to create something which is a space of couplings. So it's a discrete set of couplings. So it's a set of discrete couplings rather. It's just matrices of size n times m, non-negative, such that the row sums are equal to A and the column sums are equal to B. So this is going to be the main, the mathematical object. If you remember, the Kantorovich problem had the same setup. Now, the optimal transport problem is simply trying to minimize among all matrices that satisfies those marginal constraints, that which has the smallest Frobenius dot product with the geometry, basically, in your problem. And if you think about this, this is a very, very classic type of linear program. It's one where you have this. It's given to you in a so-called canonical form, in the sense that you're minimizing a linear product of a set of variables which are constrained to be non-negative and which have only equality constraints. So this is what people call a canonical linear program. And it's one out of many, of course, LPs. And as with every other LPs, it has a dual formulation. And you remember that I introduced a dual formulation of the Kantorovich problem in the continuous world, but it has a very simple analogy in the discrete setting. And in the discrete setting, we're going to integrate, remember the integral of phi and psi against mu and u. We're going to integrate a vector against the weights A. So it's going to be alpha transpose A plus beta transpose B. But there's going to be a constraint here on the weights, which will be that alpha I plus beta j is smaller than the distance between xi to ij. So if you remember a few slides ago, what we had is that the potential at any point x plus the second potential at any point y was smaller than the cost. Well, this is just a discrete formulation. And this gives, as I said earlier, the dual formulation is actually, it can be very, very useful. So imagine I'm going to run an optimal transport solver on this problem here. So again, so this might be also, those are sources, these are locations where some resource is produced, and those are locations where the resource is needed, and I need to find out which mine here or which location resources sends those resources to the target. And so this is the optimal transport, okay? So we know that this here has some mass. It's going to split the mass here. This one is going to go there. This one goes there mostly, and this one goes here. So this is the solution that you would get in the primal. So what is the solution that you get in the dual? Well, the dual is a bit different. What it does is it tries to maximize those two dot products who are subject to constraints. But what is important to see here is that we're going to look for a value at each point of the input measure and another value at each point of the output measure, okay, or the source and the target measure. So here I've plotted those values for each of those of the dots in the inputs and the squares in the target. And so what you observe here is that if you have a color map here, at those points in the input source, it seems that the values are quite high. Then you have values for the target, which are also distributed according to something where this seems to be quite low and the value that is there is quite high. And so essentially this is telling you, because the cost of the dual, the maximization, is the same as the minimization of the primal, here we're adopting a perspective where we're trying to minimize cost. Here it's a perspective where we're trying to maximize prices somewhat under some constraints. And what you see here is that the reason those values are higher is essentially because they contribute more to the optimal problem's cost, basically, the total cost. This means that this is, from the perspective of a planner, this is how I want to send things. From the perspective of a budget, person that is an accountant, this is basically how costly it is, how each of those locations is contributing to the overall cost of moving mass. And what this tells me is that actually that point is kind of messing things up. This one is also messing things up because it's very costly relative to the input ones. Those ones are okay, seem to be doing fine. Whereas here, the same thing applies. Those points here have a low price. So here the price is, analogy is a bit, the price here can be negative. It's quite classical in linear programming. But the only thing that matters is really the relative ordering. And so those points here have a low price, which means that it's not too costly to transport, whereas this one is actually messing things up. So the dual problem basically tells you what points in the transport, in the support of the input and the target measure, are actually contributing the most to the Wasserstein distance. So it's very clear that if you want to find a way, for instance, to reduce the distance between those 2-point clouds, if you were to be able to move around, a factory or a destination to reduce the Wasserstein distance between the two, it's the dual that you should be looking at. Because you're going to say, okay, this guy is very, very expensive, so maybe I want to make it closer to everyone else. So now, let me just say that if you look at the geometry of the problem, this is a classic LP. So the set of matrices that satisfy the marginal constraints is a polytope. So it's a bounded convex set, a bounded polyhedron. And the matrix of cost is just one vector. So here you have to imagine that we are in a space of matrices of size n times m. And the goal of linear programming in this case is just to find among all the points here that which has the smallest dot product with this thing here. And that's, of course, going to be this one. Now, the reason I was saying that computationally optimal transport is challenging is that this problem actually, it looks very simple, but it has drawn the minds, the most impressive minds of the second half of the 20th century, because when people started to propose linear programs and network simplex solvers, this triggered a lot of research into trying to find better algorithms. And right now, the understanding is that there are algorithms that are provably n cubed log n. So if it's n and m are different, this will be n plus m and m log n plus m that work for this problem. So we were able to prove that. Of course, this is just complexity bounds. So typically, algorithms might be a bit faster. But indeed, you can see that if you have to instantiate a network simplex solver to solve an optimal transport problem, the one that I just described here, or for that matter, this one as well, then you will need to wait for quite a long time if you have, let's say, more than 20,000 points. And this is a problem, of course, in machine learning, because typically the measures that we're going to compare can be a lot bigger than 20,000. But there is another problem, which I think is a bit more insidious, which is the following. Think about this. Okay, so you have this setup where you have given a measure mu and a measure nu, so it has point x and a point y's, weights a's and weights b. You run your network simplex, you get to the optimal transport, and the Wasserstein distance is basically, you remember, is just the dot product between this matrix and this. Okay, so it's going to be basically the value here on this real line. Now, if you only do this as a one-shot operation, that's fine. I mean, it will take some time, but you can do this. What happens, though, in machine learning very often is that we are interested in trying to differentiate that quantity. Maybe we have this Wasserstein distance and we want to make it smaller. So we're going to look for slight variations of our inputs and see if they translate to a decrease in the Wasserstein distance. And one of the problems with LPs is that this is not, they are intrinsically not differentiable for this, because the solution, the optimal transport solution, is not necessarily always unique. And let me just illustrate this. So imagine I start changing a little bit my x, I'm adding some deltas to the locations. Then this never really happens in practice, but you might very well be in a situation where your constant matrix, the distance, is actually orthogonal to a facet of this polytope. And so all of a sudden you go from one corner of this polytope of solutions to all of the points in one facet are optimal. And then what happens is that if you keep on moving a little bit, with your data, you will switch to a different corner of the polytope. So to be clear, this thing here will very, very rarely happen in practice, and it doesn't really, it's not a headache, if you want, to think that sometimes the solution is not unique. What is a headache, though, is to see that sometimes we switch from this optimal transport matrix, which is a matrix which usually has a lot of zeros, to one all of a sudden that will be different and will be in a different corner, just because we have changed slightly the values of x. And so, in other words, if you instantiate it on discrete data, the Wasserstein distance between two discrete measures is not differentiable. It will have a sub-gradient, somewhat. You will be able to linearize it locally, but there will be some issues associated with this. And so this is the first thing is computations. The second thing is this lack of differentiability. And the third thing, and this is really goes hand in hand, I'm more or less describing over and over the same thing. The program that will output the optimal transport will actually be very hard to parallelize. It will essentially be, if for those of you who are familiar with linear program solvers, it's a long series of discrete operations, typically pivoting around some variables, putting variables in an active set and removing variables in another active set with some pivoting rules. And this was one of the first implementations of the Earth-movers distance of this that impacted the computer vision. And here I'm just showing that this is actually not a simple algorithm. It's a few hundred lines, and this is arguably a very lightweight implementation. If you look at implementations that are actually being used right now, they're typically a few more thousand lines so that they can take advantage of some speedups. But so to summarize, three main things about solving transport in a discrete manner. It doesn't scale, at least complexity-wise, but also in practice, you can see that there's a wall. It's not differentiable with respect to inputs, and it's typically something you wouldn't be able to run on GPUs or TPUs or parallel hardware. It's going to be just, you can only use naive parallelization, one CPU per pair of measures that you're going to compare. So this is why, if you were to actually stick to that way of solving optimal transport, I think we wouldn't have made a lot of progress. And this is why people keep on regularizing or changing the terms, of this optimization problem. Maybe you can do a short break for questions.
Okay, so are there any questions?
So I wanted to ask one.
Okay, go ahead.
So you discussed this sliced Wasserstein distance. So in that paper, do they also, this looks simple because in one dimension things become like much more simpler than like solving this in like high dimension. So do they also provide this approximation guarantees? Like, I mean, well, the intuitively, like, what's the, like, how far it is from the true Wasserstein distance, or?
No, so there's two ways I can take your question. So the first is, imagine that you have two sets of values on the real line, or actual or densities actually. The formula that I gave here is exact. That is, you could go and instantiate this transportation problem on mu and nu the way, and look at all the couplings in R2 and optimize over all the space of couplings in R2, etc. But that would be useless in this case, when the cost as this or this property, because actually the quantity is given to you in closed form, and you also have access to the optimal transport. So again, this is a slight bug. This is a transport between from nu to mu. You should just switch mu and nu to have it from mu to nu. So this is an exact formula. There's no approximation. Now, if you are talking about, I have discrete densities that are samples from continuous densities, I can also compute generalized quantized function and integrate their differences. And if you're asking how far is that from the true distance between the true densities, then there are some results.
I asked about the sliced Wasserstein distance.
Like sorry, apologies. Yeah, I think I wrote here certainly not optimal transport.
But like not even close, like no approximation guarantee, like in what case it?
Yeah, I mean, if you were to find approximations, I'm pretty sure they would be very, very poor. So the simple argument for this is that this will be a Hilbertian metric if you set C to be something that looks like a metric. So it will be living in the space of Hilbertian metrics and constrained to stay there, whereas transport is not one. So I'm pretty sure that the higher in dimensions you go, the easier it becomes to find counter examples with huge distortion.
Okay, I see.
Now in 2D, 3D, you couldn't. If you're unbounded, you can also find distortion, I think. Sure. But in practice, empirically, it seems to work quite well.
Okay.
Sorry.
Okay. So maybe we take one more question and then move on. And the next question was by Hugo in the chat, and he asked whether it's clear that it doesn't work for mixtures of Gaussian, that you can write down an explicit transportation plan.
Yes, it's clear that you cannot. Basically, intuitively, if your Gaussians are very thin, very concentrated, then you're going to increasingly look like the classic optimal transport problem. And so there's not going to be an easy way. So what you can do, and what people do a lot, is they see Gaussians, mixtures of Gaussians, as discrete measures on the space of Gaussians. So it's just a few points in the space of measures. And then they use this burst distance between Gaussians to instantiate an optimal transport problem. So if you have, let's say, k Gaussians and k Gaussians, you would compute a k squared distance matrix between those Gaussians, and then run optimal transport on that, as if basically they were not communicating with each other. So this approximation works if the Gaussians are quite concentrated. When they start being more diffuse and overlap each other, then this doesn't really work. So there's been a few papers on this. So let's say that there is an easy upper bound that you can come up with, but to my knowledge, you could find counterexamples where it significantly degrades.
Okay, then I'll suggest we continue. And
okay, so I'm going back to section 3. So I wanted to start this section with what I call here a reality check, because at this point it's been maybe 2 hours and so that you've been hearing about Wasserstein. So the first part I mentioned is great, the theory is great, people like it, and lots of Fields medals. Then I started diving into how to compute it, and I think you can argue that those were somewhat disappointing results, because the only cases where this is easy to compute is basically univariate. Okay, so you can use slides. That's a nice trick. Gaussians, but as we just discussed, this doesn't extend to mixtures. So we're a bit like, it's a bit as if we were playing with a KL, I mean, the same kind of invitations. And then I showed very bad results in terms of computations, right? Because I told you that basically, essentially, this is cubic, and it doesn't parallelize well, and it's not very stable. It's not smooth, so you can't differentiate with it. So there's a bit of a disconnect between the nice rosy picture I gave in the beginning and now all of what I'm saying. And so let me add yet another pessimistic take on all this before I actually show that the regularization helps. So if you think about this Wasserstein distance, if you want to convince friends in machine learning that this is useful, there's a variety of arguments that you can come up with, but essentially they will boil down to two types of arguments. It's either a computational one, and maybe performance-wise, and what would people call statistical property. So the performance is a bit, encapsulates both those things. The performance in practice is how fast it is and basically how reliable and whether the performance is, the classification or whatever is good. So you can break down those into computational and statistical. So the first one is essentially how long does it take for me to compute the Wasserstein distance or whatever proxy between two discrete measures that are samples from an underlying distribution. And the second is the statistical in the sense that, okay, I might devote some effort to compute that, but the question is how close is it to the actual true quantity that I'm trying to deal with? If you're trying to, let's say, evaluate the Wasserstein distance between mu and nu, the only thing you have access to is samples, and you could compute the Wasserstein distance between samples, but there's no guarantee at all that this Wasserstein distance between samples is in any way related to the Wasserstein distance between densities, then maybe this was not really worth the effort. And the way you would typically have results is essentially, is there a way to bound on expectation with respect to the samples, the difference between the Wasserstein distance between the two measures and the one from samples as a function of the size of the samples from it. So you would like to see a decrease in this difference as n and n increase. So on the first front, I already told you something quite bad, which is that essentially, if I want to approximate this the way, the linear programming way, using samples, well, this is going to cost me a lot. The second part is actually almost, I could say, even worse, because actually it's known. So there's a long list of results here. So as you can imagine, it will typically depend on assumptions that you make on mu and nu, assumptions that you make on the space, assumptions that you make on the costs. So there's lots of relevant setups. But let's say the main one, which would be high dimension, Euclidean cost, square Euclidean cost, is very, very pessimistic. It says that on expectation, the difference between the Wasserstein distance of two continuous measures, mu and nu, and their sample estimates, so the population estimate and the sample estimate, the difference on expectation is basically of the order of 1 over n to the power 1 over d. So this will decrease extremely slowly in high dimensions. Okay. So if you're in dimension 10, you would need power 10 more samples to get an improvement in this estimation. And so there's a long list of long literature, and as I was saying, people are trying to narrow down on more precise results. Essentially, why this is this way is also related to quantization error problems. Imagine that you want to quantize the uniform measure on the hypercube in dimension, let's say 10, with a few atoms. So this would be as being able to actually look at where those samples are. But you will see that the quantization error in terms of even on this very simple setup where you're actually free to choose the best possible approximation, discrete approximation of your measure using quantization, it's still going to be of this order. So there's a barrier there that we can't really get rid of. So you are a machine learning person, you like Wasserstein, you like optimal transfer because the ideas are neat, and you go to your colleague next door and the colleague asks you, well, how long does it take to compute, and what are the properties statistically? And they say, okay, this and this. Then the debate is over, and there's no need to actually talk about optimal transport because it's useless. And of course, the end of the story is a bit more optimistic. The end of the story is that those two results essentially come from the fact that we are sticking to the linear programming formulation that Kantorovich defined about 80 years ago. And so this linear programming formulation works for continuous densities very well, but it doesn't work for computational purposes when you are actually playing with samples. It doesn't work both computationally because it's too costly, and it doesn't work statistically because it's basically overfitting the samples. It's trying to work too hard by really looking at this very narrow corner of the polytope that gives you the optimal solution. So the reason why optimal transport works in machine learning, whenever you see a paper that cites it, is rarely going to be because it sticks to the original formulation. It's always, or nearly almost always, going to be because it regularizes the optimal transport in a way or another. It changes basically the way the problem was defined. And if you think about it, you can change many things here. And I think I mentioned this yesterday. This is just an optimization problem after all. So we are free to actually start playing with all its elements. So for instance, if you start saying, I want to constrain the set of potentials here in the dual problem to an RKHS, then you can see that this will provide you a smoother approach, a smoother problem, and then you can show that there are better statistical properties. And this is related to entropic regularization that we'll describe later. You can also say, well, actually, this Wasserstein setup with square Euclidean distances or more general constants is too complicated. I will use this Kantorovich duality, which tells me that in this particular case where the cost is a distance, then it's the same thing as optimizing over one Lipschitz functions. And it's actually simpler because I only have one potential to deal with. And now imagine that I introduce yet another trick and I say, well, maybe optimizing over one Lipschitz function is too complicated. I'm going to somewhat optimize over somewhat Lipschitz functions by design. And that could be, for instance, ReLU, deep networks with ReLU activations. You can also think about the improved Wasserstein GANs as yet another regularization where I'm going to add a weight on the scale of how often the gradient of phi is from 1, the normal of the gradient of phi. So you can start adding every flavor of regularization you can think of. And the same thing applies here for an approximation that was proposed much earlier of this Wasserstein 1, which was using wavelet decompositions. Basically, it was saying, well, a function phi that is one Lipschitz has a certain wavelet decomposition that could be constrained in such and such ways. So, of course, what I want to insist on is every time we change something, we're departing from the orthodox formulation of the Wasserstein distance. But I think it doesn't matter. I think it's okay, and it's something that we should do because it's provably wrong to actually use the original formulation of optimal transport, in the sense that in statistical terms, it's a disaster. You could maybe, even if you were able to cope with cubic computations because we have a lot of resources, the fact that the sample complexity scales exponentially just makes it irrelevant somewhat to applications. So we need to do something. Then we can also regularize the primal problem. So in the primal problem, an important research direction was to, even before this was understood, was to somewhat limit the scope of the cost. So yesterday we had a discussion with participants about this. So maybe an obvious way is to threshold, for instance, the metric. And this was proposed in a computer vision paper a few years ago. Or you can start actually enforcing that the cost has a very specific structure, such as the shortest path distance on a graph or things like that. And this simplifies the LP, makes it faster, and also works better statistically. Now, the other thing you could do is change the way the measures are inputted to your solver. So this is generic. Of course, this is mu and u, whatever. But if you're giving me samples, maybe I could quantize them first. So imagine that you start with, you give me 10,000 points and 10,000 points. I run k-means on both with k equals 100. This reduces a lot the size of the problem and also brings statistical stability. So it's not so stupid per se, if the only thing you want to do is compute the Wasserstein distance, to run k-means first and compute the distance between the k-mean centroids. So you could also cast the measures as Gaussians. So we mentioned this. Then in that case, it's easy to compute. You could project on random lines, and this was the idea of I already introduced of the slice. Or you could also project in k-dimensional subspaces. And so there's a fertile ground there to actually look at what are the good subspaces that you could project the measures onto before evaluating the Wasserstein distance. And the other thing is you could add priors on the coupling. And this is what I'm going to talk mostly about in the next slides. You could say maybe just taking any coupling is just too unconstrained. I had this polytope of couplings. Somewhat I need to choose a smoother, smaller ball in which to choose my couplings. And this can be achieved by adding regularization of any sort. This could be adding the squared Euclidean regularization, the square norms of P, thresholding, upper bounding the entries of P, etc. There's many ways to do that. So which takes me to this entropic regularization scheme, which has been the engine of many of the applications that you can see recently. And the intuition for this is actually simple. It's if we're sweating so much to get to this corner of the polytope, it's because essentially we're really taking for granted all the data, x, y, a, and b. So earlier on, I think you remember I was changing a little bit this the direction of this vector and showing that there was instability. But actually, the same thing applies exactly for a and b. If I were to change a little bit the weights, this polytope would start wiggling around, and then all of a sudden, it will hit a different face. So what you want to do is trade off that precision, that optimality, for something that is a bit faster and a bit more stable with respect to the inputs. And this is just textbook regularization. And the other thing that I want to get as a benefit, and I will get a bit later to that, is also something that is differentiable. By smoothing, basically the problem, you want to get something that is a unique solution, not necessarily one that can be degenerate and have an infinite number of solutions, and something that is also easier to compute algorithmically so that you could put it in your PyTorch or TensorFlow or JAX or whatever autodiff pipeline. So this is a big wish list. And it turns out that there's one simple way to tick all the boxes. So there are other regularizations, but for some reason, they don't necessarily fulfill the entire wish list. The entropic one is quite remarkable in that sense. And let me say that this idea is fairly old, actually. And historically, it's interesting to see why it appeared. It appeared essentially because when people were running optimal transport, this was mentioned yesterday in a question. When was this used for? What was it used for in the first years? And it was used first in economics, where people were trying to predict patterns of transportation from marginals. They would look at, okay, this is where people live, this is where they work on aggregate. What should I expect the traffic to be between those points if people were following optimal transport? And what people were looking at is that people were not following optimal transport. They were a bit messier. Somewhat they were optimizing a bit, but there was no way they could actually be on that corner. And so you would see traffic that was a bit blurry. And so people started thinking, okay, if we can't predict what happens with optimal transport only, let's actually embed some fuzziness in the LP, put it there, and then hopefully the result of our fuzzy LP will look a bit more like the fuzzy reality that we see. And so all of this is summarized in this line. This is the linear program that was given before, the coupling with the marginal constraints and dot product between the coupling and the cost matrix. And what we're just adding is this minus gamma entropy of P. So the entropy is in the simplex. So remember that P here is a matrix that sums to A in the rows and sums to B in the columns, which means that it sums to 1 overall. So it's a probability distribution, it's a coupling. So you can define its Shannon entropy. So this is just the entropy. So the entropy on the simplex is 1 strongly concave. So if you throw minus gamma times the entropy of P, you will have a gamma strongly convex regularizer here. So this is a linear program as long as gamma is 0, and then when gamma is strictly positive, then this becomes a strongly convex problem. And so because it's a strongly convex problem, if gamma is strictly positive, then we have a unique solution. It's strongly convex inside a bounded polyhedron. And so this is what it looks like. So this is distribution mu, and this is distribution u. Obviously, for computational purposes, I've discretized them over a grid of, let's say, 100. And this is the optimal transport C. As you can see, it's very, very thin. It's almost impossible to look at this. I mean, it's very hard to actually notice the areas where there is weight. So I can draw a line on top of it. So essentially what you get is when you run the LP, you're running an LP with 100 times 100 variables. This is a coupling, so 10,000 numbers. And it turns out that the sparsity of the solution is very large. There's a very big sparsity because this is a simple result from linear programming. If you have 10,000 variables, but you only have 100 plus 100 constraints, then at most, the optimal solution will have 200 non-zero variables. And so here, or better said, you will find a solution that has up to 200 non-zero variables. And what you can see here is that we're basically on the limit between the Monge and the Kantorovich problem. This is still a coupling, but it's full of zeros everywhere, and it's very thin. It looks like a ridge. And so it basically says, well, whatever mass that you have here, you should allocate it here, for instance. Whatever mass you have here, you should allocate it here. So it's almost as if this was a one-to-one correspondence, not so much a coupling. When you throw in a regularization, this is not possible. This is not good. Because a matrix with a lot of zeros and just a few values that are positive has very low entropy. And remember that we want big entropy here because of the minus here. We're minimizing, but with a minus in front of the entropy sign function. So we want big entropy. So of course, if gamma is very small, the trade-off between whether this has entropy or low cost will mostly go for the low cost. And so what you will start seeing is a bit of a diffusion, a blur that starts popping up on the original curve. However, this blur is not isotropic. It's not as if you were, blurring the entire curve point by point. And the reason this is not so is because we still need to satisfy the marginal constraints. So if I were to blur everything in this point, typically, for instance, I would start creating mass that is not there, or requiring mass that is not there, or creating mass that is not there. Or the same thing would apply here. If I were to blur this with a small Gaussian blur here all around it, then I would be creating too much mass here. So you need to still blur, but in a clever way. And this is why you still let blur kind of pops up in areas where you can, and then there's no blur in areas where you cannot actually. And the bigger the gamma, eventually, you will start seeing that blur become more and more pronounced, but still not blurring in areas where you can't. Until in the end, you're essentially looking for the maximal entropy distribution with marginals mu and u, and that's simply the product of the marginals. So you have this kind of path, regularization path that goes from Kantorovich, which is also already itself a bit to the right, if you want, of Monge. You could be plotting Monge somewhere a bit even further left, but Monge will be degenerate and won't work in some cases. Here we're more Kantorovich, so there might be some mass splitting. Some lines might be might have different values, and then we're gradually going from this to basically the product of the marginals. And this is what energy distance corresponds to. The product of the marginals is just simply, this was the idea of the naive general that would say, whenever I'm going to send troops, I'm just going to split everything proportionally. Whenever I have mass, this mass, I split it proportionally to whatever I have here in the second margin. So neat, that sounds like a nice explanation, and we've kind of connected many dots, Monge, Kantorovich, and energy distances. How does this work? Well, it turns out this is the nice surprise. This is computationally extremely effective. And the reason is that if you just write first order conditions for this problem, and I've just written them here. So the first order condition would just be the objective, which is the dot product, the neg entropy scaled by gamma, plus now the Lagrange multipliers for the constraints of being the row sum equal to A and the column sum equal to B. Notice I don't need to add the constraint that P is non-negative because of this of the log here. There's a Pij log Pij basically makes sure that this can't go below 0. It can be 0 because this is not going to blow up at 0, but it cannot go below 0. And now if you just take the derivative of this with respect to Pij's and set it to 0, you will just see that you need to have a solution that I call here P gamma, the argument of this, that is defined as, on the one hand, a constant that depends on the, a value that depends on I, another value that depends on J, the index, and then something in the middle which depends on Ij, which is given to you by the problem. This is not optimized. So here I wrote this K matrix, bicolor one, to insist on the fact that this K matrix is given to you as a result of taking the exponential element-wise of minus the metric between X and Y. So this is it's not coincident that this is called K. This is really a kernel matrix, actually. It would be positive definite if this cost function was negative definite. And if it's a squared Euclidean distance, of course, you can see a parallel. This is a Gaussian kernel matrix, a pairwise Gaussian kernel matrix. So you have this kernel matrix K here. And what first order conditions tell you is that there must exist a vector U and a vector V such that are non-negative, such that P gamma is the diagonal matrix times U of U, times K times diagonal matrix of V. So this is UI, Kij, Vj. So the only thing you need to solve here, this problem, is find two vectors U and V such that, basically this is the first order condition that we need to use the constraints. This matrix here has the right row sums and column sums. And by row sums, I mean that if I multiply by 1, I get A. And if I multiply the transpose of this matrix, which is easy, it's just diagonal of V, K transpose diagonal of U, I get B. So let me just simplify a bit those two identities. So we're looking for U and V that satisfy this. So diagonal of a matrix times a vector of 1s is just or diagonal here U times the vector 1 is just simply the vector itself. Okay, diagonal matrix times the vector of 1 is just going to be the vector. And so this simplifies. So what we have now is a diagonal matrix times a vector. So this is a vector. So this is just a diagonal matrix times a vector. So it's just the element-wise product of two vectors. So we are down to the point where we need U and V to satisfy those two equations. And actually, maybe it's a bit simpler if you write them in the following way. It's going to be U is equal to A divided by KV, and V is equal to B divided by K transpose U. So those two, here, I want to keep track of the fact that the only variables that we have here are U and V. A and K are given by data. So the only thing you need to find is, those are basically two nonlinear equations that you want to solve. And there's a very simple approach to solving it, and it's provably convergent, and it's called Sinkhorn's algorithm. It's basically repeating the iteration that U is set exactly so that A is equal to A divided by a KV. You initialize V randomly. And next, V is set so that B is equal to B divided by K transpose U. V is equal to B divided by K transpose U. And if you iterate this, in the end, you will converge to a solution that will satisfy exactly this. So not only will you do that, but the speed of convergence is actually quite well understood. So Sinkhorn proved first that the convergence was guaranteed. Let me just say that this algorithm actually dates back to further to before. And this was called the RAS algorithm in economics. IPFP also, iterative proportional fitting procedure. There are several names, but Sinkhorn, it's usually associated to Sinkhorn because he proved first that it was a fixed point, a convergence fixed point iteration. And then there have been a few results in the literature that you can find on how to quantify the convergence of this algorithm. And recently, because of this interest in the Sinkhorn algorithm as an engine to solve transport, there's been a few more refined results that have been appearing recently. So one thing that you should notice, and is really important, is that essentially what I've just provided you is a simple way to compute transport, or at least approximate transport. So keep in mind that we want to solve this for a certain gamma. And I'm essentially saying that the solution must be of this form. And I'm giving you an algorithm to compute what is missing here, which is U and V. Okay, and the U and V, you just get them by repeating this iteration. What exactly are we doing at that iteration? Well, if you look at that iteration, this is a vector of size n. This is a matrix of size n times m multiplied by vectors of size m. So the main computational effort here is this kernel multiplication. The division here is linear in the size. This is just quadratic. This is just O n m. Every time you apply this kernel, you would pay a price n m. And every time you apply the transpose, you would also pay a price n m. So the big challenge is, can we bring this down further? But the one thing maybe that is worth noting is that even if we can bring this down further, this is already a set of operations that modern hardware is extremely well equipped to deal with. So GPUs, the entire goal of GPUs is to do matrix products quickly. And so with this iteration, we can now approximate optimal transport with something that only requires calling matrix products and element-wise divisions. So it's trivial from a bookkeeping perspective. It's just starting with a vector v and just running those iterations. And you can show, of course, whenever you do a matrix vector product, you should ask yourself whether there's a faster way to do it. And there's been a few works on this. So in some settings, this is actually, well, I should be a bit more precise. This is really not really n log n. This is slightly, it's n to the power 1 plus 1 over d, where d is the dimension of the space. So asymptotically becomes log n. But there's been work on actually going down to really n log n using hierarchies. I will add the reference. This was published a few weeks ago in the slide. So maybe I would like to give you a feel of what this algorithm does, so that we're clear. Essentially, this is the data on the left. This is something I won't touch for now. And this is what the algorithm does. It just initializes a v0, which is a vector of the same size as b, and just applies the kernel to it, the kernel matrix K, and just take element-wise divisions of two vectors of size n. So this is my vector u1. This is what I get upon the first iteration. And then I can continue like this. I just apply K transpose, take B divided by this vector, and this gives me V1. And I can do this over and over again. As you can see, this part doesn't change. The A, B, and K is never going to is not moving. It's just basically applying those operations like this. So this is trivial in terms of coding. It's just 2 lines of code. What is a bit more interesting, I think, from an implementation point of view, and this is actually what really motivated me to write the paper in 2013, is that this is, it's not only embarrassingly parallel, it's just something that you can actually speed up using matrix operations rather than matrix vector operations. So very often, also, let me just keep this. This is saying how you get the solution, how you get the cost. But in practice, in machine learning, we rarely need to compare two histograms. We're often dealing with a lot of histograms, and we want to compute simultaneously the distances between many pairs. So maybe I might want to compute the distance between this one and this one, this one, this one, etc. So in that sense, you can very easily cast. So now this is very obvious. All of this as a tensor operation, as a matrix operation. So you will instead of initializing a single vector of potentials, of V0s, of scalings, you will initialize a matrix of scalings that will correspond to all of the pairs that you're trying to compare. And so you would do this in the same way that I did it before. And so this makes it very, very convenient for large-scale computations. So this was a slide, this was a figure from the original paper in 2013 that was showing significant speedups over LP approaches. This is still relevant, and of course you can start shifting the curves in both directions because everything it would be faster. But essentially, if you throw in regularization, you can very easily find examples where solving with a Sinkhorn algorithm is thousands of times faster than solving it with an LP solver. Now, to continue a bit with a few simple examples, but I will be fast on this one. this is what would happen, for instance, if you were to transport two measures, which are the minist digits. So in one digit you have mass, which is concentrated in this square, and the other digit you have mass distributed differently on the square. And I'm going to use the distance, which is simply the squared Euclidean distance between them. So the way you would run Sinkhorn here is just simply starting by setting a V1 scaling, which has the same shape of B than B with noise. And then what you do is you apply the kernel. Remember, the kernel here would be, so if this is 20 times 20, this means that there are 400 pixels. The kernel will be this big matrix of size 400 times 400. But here it turns out this is also why you can actually cast this as something faster than quadratic when you're playing with grids. Here, this kernel, if you really dig a bit, it's just a Gaussian blur. So applying the kernel in this case is just like blurring this potential. And now I'm going to take the inverse A and divide it by this thing here. So I'm dividing those values by these values. So the one thing you should start noticing is that because some of the values here are 0, then we will have a lot of zeros here. And then you will be dividing this density by this density here pointwise. So luckily here, most of the values on the top are much bigger than the values on the bottom. So you will essentially see something that behaves well. But in the next iteration, so this was for the first potential that went from V to U, I am going to apply a Gaussian blur again on this potential, and now take B divided by this. And this starts becoming a bit more tricky, because as you can see, you will see some values that are very close to 0 in those areas that you will be putting in the bottom as a denominator. And here the numerator will be this. So you will see values that seem to start to diverge. And that's not a bug. It's actually the way the Sinkhorn algorithm works. It's normal that you have 10 to the power 8 values that start popping up. And so here it's actually dominated by just this one here. This is a value that is 0.015 divided by something that's very close to 0. So small, but divided by 0 pops up. And so if you continue like this, essentially Sinkhorn seems to be completely bugging in this setup. But that's normal, actually. And so if you experience issues with Sinkhorn, they probably come from that. Now, the reason why this seems buggy, but it's not, is that we should be looking at all of this in the log space, which is why a lot of the stabilizations procedures for Sinkhorn that have been proposed recently rely essentially on the log formulation. And so if you take the logarithm of those scalings, essentially what you start observing is something that looks like the dual variables that I introduced a bit earlier. Here, what you see is essentially popping up as a logarithmic value. The high values are those areas where the transport is actually costly to carry out. And it's clear that if you want to carry out a transport between this digit and this one, what will be costly will be to move around the mass here so that it goes somewhere around here, and maybe the mass here so that it goes somewhere there. And for the one, it's going to be the same thing. So you start seeing basically so just to give you some hints, basically the scalings that pop up in Sinkhorn, if you take the logarithm, you can associate it with the potentials of the dual Kantorovich formulation. So here I've plotted the transport, but it's not so easy to visualize. What is easy to visualize is that at each iteration, the marginal violation, the fact that the matrix that you're computing here is increasingly closer in terms of marginals from the target. So I think I'm getting closer to the end of the talk. So I have many more slides that I want.
7 minutes left. So.
Yeah, but if I want to take maybe a few, or maybe
including Q&A here.
But maybe the questions I can take them from 11. Maybe it's easier.
Yeah, that's true. Yeah.
Yeah. So I would just flip a few slides. I'm sorry if this is a bit fast, but I want to cover a bit this material. So this is just no. I'm not going to cover this. I'm going to cover this relationship between MMD and optimal transport because I've talked about it a bit earlier. So to recap, if you give me two measures, weights A's and locations X, B's and Y's, the optimal transport problem, the classical way, Kantorovich formulation, is this polytope. You have the cost direction, which is given to you with the matrix, and then you just try to hit the corner. What essentially I introduced is a new solution that is suboptimal, but is optimal with respect to entropy. It has both a bit of low cost and a bit of high entropy. And the other thing that I mentioned is that if you actually only care about entropy, you will eventually converge to the product of the marginals. Now, if you move around with gamma, you have this regularization path that will give you access to a family, different family of optimal transport plans. Now, let's compare a bit what we can do with those three things. So I'm just including now, to be clear, the entropy within my definition of a smooth Wasserstein distance. So a regularized Wasserstein distance. So on the one hand, you have this cost. Okay, it's just the transportation costs of the coupling, independent coupling. You have the transportation cost of the smooth problem with the entropy of the coupling, and then this never changes. This is just the optimal transport that you get. And I'm going to do a small polarization identity to make sure that this is basically equal to 0 when mu is equal to nu. So I'm going to define the energy distance, and you can see that this corresponds to actual definition of energy distance, as this function of mu nu minus half of what happens if you just say, if you try it on mu and mu and nu and nu. And I'm going to do the same thing for this smooth regularized Wasserstein distance here. It turns out that you can actually interpolate between the energy distance and the Wasserstein distance using this object here in the middle with this cursor of playing with gamma. And what is actually interesting, if you remember our argument a few slides back, is that in terms of what people like, computational and statistical complexity, well, MMD is hard to beat because it's just basically instantiating this cost matrix and summing it. So it's very simple. It is also very efficient from a statistical perspective. But somewhat, it's doing something very simple. Therefore, it's good statistically. It's not surprising. Here, we're doing something very useful and complicated. So we pay a price computationally, but it's overfitting from a statistical perspective. And so what we are able to show in recent works is that, well, the Sinkhorn algorithm is what gets you to this quadratic complexity in terms of computations. But recently, we're also able to show that you can also get a nice statistical sample complexity using the Sinkhorn approach. And there are other nice properties that have been proved, such as the fact that this is always positive, that it is convex in some of the arguments, etc., etc. And the last thing I want to emphasize is differentiability. So by differentiability, I mean, okay, it's fine, we can compute this quickly. The question I want to ask is, what happens if you change a little bit the weights of the measures? Can you compute somewhat a linear approximation of that? And what happens if I change a little bit the locations? And for this, my short answer will be, there are papers that study this from a convex analysis point of view, and there are lots of nice results. But in the current world, maybe one of the simplest way to look at this is as a programmer. We just instantiate a program that runs the Sinkhorn iterations in the following way. Just start with the naive initialization, run Sinkhorn using your data, and then you just backpropagate through all this whenever you want to change any of the arguments. So that could be X, Y, A, B, the parameters of your cost in the kernel, anything. So essentially, Sinkhorn is just a stacked neural network where all of the intermediate layers are matrix vector products or element-wise inversions, and all of the layers basically share parameters. So that's going to close the lecture. Maybe if there's time, maybe for 1 or 2 questions.
Yeah, thank you very much. This was amazing. So let's take one question. Vivek wanted to ask a question. Okay, 1 second. Okay, go ahead. You should be able to talk now.
You are muted, Vivek.
Yeah. So my question is, like, you already pointed out some connection of optimal transport with k-mean clustering. And you also talk about entropy regularize optimal transport. So is that anything connected with like fuzzy clustering and all? And what is the equivalent of, like, if we have constrained like sparsity in clustering, like dictionary learning or something? How is that connected to optimal transport? Is there any equivalence in that form also?
Yeah, so this is a very interesting question. So the link between optimal transport and clustering is the following. When you're doing optimal transport, you both need to know where you're going to transport, this is locations, and what are the weights. So if I wanted to give you a simple analogy, imagine you have a map and you have people, and you want to place food trucks on the map. If you were to run a clustering algorithm on where people are to find out where you should put the food trucks, typically k-means, this would lead to a situation where potentially a food truck, a cluster might hold a lot of people. And some food trucks that would be maybe placed somewhere in the outliers might only serve 2 or 3 people. So somewhat, when you do clustering, you don't really care about the capacities of each cluster. And if this is something you don't care, it's as if you are doing transport, but you are actually saying, I don't care what are the weights of the target measure. Somewhat, I'm just specifying where it is. And when you start putting transport in the equation, it's as if you really wanted to actually not only control where the locations are, but also the capacity of each cluster. And so this is why there is link between k-means and optimal transport. But somewhat optimal transport provides something a bit more general, which helps you handle, for instance, cases where you want to put capacities on the cluster. So this is the first question between the links. And between the entropy, indeed, so there is a link between soft clustering and transport and regularized entropic transport as well. And the links is a bit the same. When we do regularize optimal transport, we are going to add some fuzziness, but we're still going to enforce the weights of the target measure. Whereas in soft clustering, just like as with k-means, we don't care whether typically you're going to assign in a soft way towards points based on the exponential minus the distance, like a soft max of a point to all of the cluster centroids. So there are links, yes. The short answer, yes.
Anything with the dictionary learning, like if we have sparsity constraint, like only few people can go to that, like particular buckets, like only k buckets they can go to or something.
So in terms of sparsity, actually, if you use the linear programming formulation of transport, sparsity is already embedded in there. So you will have that indeed the assignment is typically very sparse.
Okay, thanks a lot.
Okay, there seem to be no more question at the moment, so let us thank Marco again, and yeah, let me briefly advertise his roundtable in about 30 minutes, and I hope to see you all there. So thank you and goodbye.
Thank you.
Bye bye, Marco.